All right, before we start, does anybody have any questions about anything that we've been talking about? I think what we're going to end up doing is we're going to today finish up stoichiometry. Tomorrow, introduce titration, which is a part of the stoichiometry chapter, and then on Friday, um, we'll work through some more stoichiometry problems as well. But on Friday, we're going to start chapter 5, and then I'm going to put together lectures over the next few weeks over topics that we need to cover, because we still need to talk about the structure of the atom and electron configuration. We still need to talk about Lewis structures. We still need to talk about enthalpy and Hess's law. We still need to talk about the ideal gas law. And we also need to talk about like energy, like energy of a photon and things like that. So I'm going to go through and outline the rest of the topics. And then that way we'll know exactly where we're going. It's going to be not every entire chapter being covered, but just topics that we need to hit to make sure that when you get to part 2, that you got all the tools you need to succeed in that class. All right, so today we're going to continue on with stoichiometry, and we're going to talk about today theoretical yield. And percent yield. I should write that out. Right, both of these are very important topics. And when we talk about doing reactions, these are indispensable topics. Right? Like we have to understand what theoretical yield is, what percent yield is, and how we get to them both. So let's say we have a reaction between A and B, and that goes to C, right? Excuse me. The pollen is wearing me out. So let's say that goes to C. One of the things about chemical reactions is this, that they rarely ever go to what we call completion. So we can say this with certainty, that a reaction rarely goes to completion. And there are different different reasons for that. One reason may be operator error. Maybe you were running a reaction and you dropped a little bit of one of your star materials on the bench top. That's a legitimate reason for not having a 100% yield. Maybe there's some side reactions that happen. That'll take away from the yield of the product that you're trying to get to. If you have some side reactions going on that take away from the main product that's being formed, right? Maybe there's incomplete reactivity. Right? Maybe one of your excuse me, star materials is not activated or not highly reactive, and so it only reacts partially with the other star material to give you that product. So there are a lot of reasons why reactions don't go to completion. I'm just gonna put here reasons, right? But you rarely get a 100% yield for a given reaction, right? Now, what we do know about reactions is that there is what we call the theoretical yield. Right, the theoretical yield. And with the theoretical yield, this is the amount of product that is expected based on the limiting reactant. So this is the expected amount of product. Right. It's the expected amount of product based on the limiting reactant. So we know that the limiting reactant is going to control the yield, right? Because remember, with the limiting reactant, once it's gone, the reaction stops. Right? We know that once the limiting reactant gets consumed, the reaction is over. There's no further reactivity. Right? So your theoretical yield is always going to be based on your limiting reactant. And so when we're looking at the examples that we're going to be looking at, one of the things that we are looking at is the fact that with the limit, we have to sometimes calculate the limiting reactant to figure out which of the two reactants is limiting, right? It's not always readily apparent, as you're going to see from the examples that we do. That in some cases, you may look at a reaction and you may see the coefficients and assume that because one coefficient is lower than the other, that is limiting. And that's not the case. You have to go and investigate that. You have to go through the process, convert everything into moles, and figure out which one is going to give you the least amount of product. Because as we talked about on Monday, that's what the limiting reactant does. It is the reactant that gives you the least amount of product based on the stoichiometry. Right? So we got an example here that we're going to look at. So it's giving us the reactants, and it says potassium chlorate decomposes upon slight heating in the presence of a catalyst. So the catalyst is not shown, but we know that by definition, a catalyst, we don't have to see it because it doesn't react anyway. It's just it's a part of the reaction, but it's not a reactant. And so it's never consumed. So we don't really care about it anyway. So it says potassium chlorate decomposes upon slight heating in the presence of a catalyst according to the reaction below. So here's the reaction here. And what do we notice right away? How many reactants are there? Right? Is there A plus B, or is it just A? Right? If you notice, come on, here, there's only one reactant. So this is limiting. We don't have to calculate the limiting reactant. It's understood because there's only one reactant. All right, so now what we want to do, let's read the question. It says in a certain experiment, 40 grams of potassium chlorate is heated until it completely decomposes. What is the theoretical yield of oxygen gas? All right, so notice on the other side, this is what we're looking for. Oxygen gas is a product. And then this is the reactant. So we're trying to figure out how much oxygen we get relative to potassium chlorate. Right, so first thing we need to do is what? Somebody help me. What do I need to do first? It doesn't matter what the problem is. Every problem has a pattern or a process that you have to follow to solve it. All right, that's just part of the game. All right, so what's the first thing we need to do here to get this problem started before we do anything else? Other than balancing, but as you can see, it's already balanced. Anybody? can I use grams in my stoichiometric calculations?
Yeah.
Are you sure? How am I going to take the coefficients and ratios from the balanced equation and use that
Okay.
with
You
grams?
meant like, what do we have to convert it to? Okay.
Yes,
All right. I thought you meant
yes.
like, could we use grams, period? And I was
Oh
thinking,
yeah, we're gonna. I mean, that's what we
okay.
have, right? So we got to work with it. But when I'm doing my conversions using my stoichiometric coefficients,
You
everything
got to
has to be
convert it to
moles.
moles. Yeah. So you got to
Yes.
multiply by molar mass.
So you're going to take 40 grams of KClO3 into moles, right? And you know that moles is, and this is repetitive on purpose. If you don't learn nothing else in this class, you don't know how to convert from moles to grams and molar mass and all that stuff. It's grams over molar mass. So I'm going to put those numbers in. I'm going to say grams was 40 grams divided by the molar mass of KClO3. Let's see if we can find that out right quick. Potassium is 39.
Sir, your screen disappeared.
Did it? Oh, shucks. Hold up. Sorry about that. Zoom. I ain't reboot nothing. Zoom is trying to tell me to restart my iPad, but I'm not doing that. All right. Can't do that. And we got plenty of battery too. Thank you for letting me know. If it does that again, just say something.
I got you.
Because I'm actually running Zoom from my iPad. All right. Can you see the screen now?
It said you started screen sharing, but I don't actually see the screen.
I see the problem. It's my hotspot turned off for some reason. Hold on 1 second. What about now?
Yeah, I see it now. It just popped up.
All right, cool. Let me know if it drops again. Because I'm running this from my iPad. I normally don't do that, but I'm kind of in a tight right now. So, all right, so potassium itself is 39 grams per mole. Chlorine is 35 grams per mole. Oxygen is 16 times 3, which is going to be 48 grams per mole. All right. So when we add that up, what do we get? Is that 48 and 35 is 83 and 39? Is that 122? Is that right? That's the molecular weight of potassium chlorate.
What'd you get, sir?
122, 39, 35.
Yeah, that's what I got.
40.
That's what I got.
All right. We're going to put this number right here. 122 grams per mole. Go ahead and calculate that, the number of moles.
I got 0.328 moles.
Okay, 0.328. All right.
Yes, sir.
So that's moles of KClO3. All right. So now we're good. We can roll now, because now we can use these moles to figure out the moles of product based on the relationship between potassium chlorate and oxygen. So that's the next thing. So find the ratio and convert. Right. So the ratio here is what? What is the ratio of oxygen to potassium chlorate?
2 to 2.
So potassium chlorate is on the left, oxygen is on the right. It's 2 to 3, isn't it? Based on the
Screen just cut it
coefficient.
again. Are you so you use the mini 3 by the O instead of the big 2 behind it?
Yeah, the 2 behind it is a subscript. That's not the coefficient. You said the screen went out again?
Yeah, just popped out.
I don't know why that's happening. Let me try something. I don't want to reboot and have to stop class. I know the hotspot is still on. Come on, so I didn't have this problem this morning. I don't know why that's happening, but we're gonna just roll with it. Thank you for letting me know too.
No problem.
And if all else fails, I can always send the morning video because we did the same problem. So, but I don't want to have to do that. I want us to do our own stuff. All right. So don't do this. Don't make me cuss out here. All right. So we got 0.328 moles, and now we want to convert moles of KClO3. Hopefully that's back up. Is that back up? I think it is.
Yeah, it popped back up.
Moles of KClO3. Okay. To moles of oxygen. So we're going to use that ratio from the reaction. 3 moles of oxygen. And back to your question, anytime you're doing stoichiometry, it's always the number in front. Because I think even over the time that we've been doing this, I've been noticing you saying put a 2 behind here or a number behind here. The number in front is the coefficient. If it's a subscript, that has to do with how many atoms are present in that particular substance. So those two different things. Yeah, 2 different things. But I don't want you to mix those up and somehow miss what the coefficient is there for, because that's the whole purpose of balancing. All right, so we got 3 moles of O2. And we're going to put that over 2 moles of KClO3 times 0.328 moles of KClO3, because we want to cancel this out. Right? Go ahead, and if you got your calculator, Nazir, go ahead and run that.
I got 0.492.
All right, so 0.492 moles of O2. Right? But that's not the end of the question. It asks, what is the theoretical yield? So up here, we said the theoretical yield was the expected amount of product, but we didn't say what that amount would be measured in, right? So the theoretical yield is always in grams. Right? That's always in grams. All right. So now what do we need to do? We have moles of oxygen, but if we want the theoretical yield, that needs to be in grams of oxygen. Right. So we're going to take that number and convert it. All right. So we're going to convert moles of O2 to grams of O2. And again, we're going to use the molar mass. O2 has a molar mass of 32 grams per mole. See, Nazir, that's where that 2 comes in. because the atomic mass of oxygen is 16, but because it's diatomic in this case, it's going to be 32, right? Because it's 16 times 2. So it's going to be 32 grams per mole times 0.492 moles. So moles are going to cancel. I'll be left with grams. So in this case, this is about half of 32. So somewhere around 15, 16 grams. Anybody got it? It's 15 point something. So it's 15.84 grams of O2. Any questions about that? So we had to first convert potassium chlorate into moles. And then once we had that in moles, we could take those moles and turn them into any of the other substances in the equation, as long as we know the ratio between the substances, which we took from the equation after it was balanced. So 3 moles of oxygen is the same as 2 moles of potassium chlorate. So once we do that, then we found the number of moles of oxygen, took that, and to get the theoretical yield, that has to be in grams. So took the moles of oxygen and turned it back into grams, right? The other part, it says in the question is this. It says oxygen gas is collected. The mass is found to be 14.9 grams.
It is. It's too many people in here.
All right. So that 14.9 grams.
Anything.
Can you mute your mic, please? That 14.9 grams is what we call the actual yield.
Okay.
Can you mute your mic, please? All right, that's the actual yield. So the way we go from actual, well, let me not say go from. The way we apply the actual and the theoretical is in calculating what we call the percent. All right. So the way we will apply this is by calculating what's called a percent. So the percent yield, come on, Zoom, tighten up, over theoretical. So that's actual over theoretical times 100. All right. And that's how we calculate. That's the purpose of calculating the theoretical. Because every reaction you do, at the end of it, you're going to isolate a product, and you're going to take that product and weigh it out and get the mass of the product and figure out how much you have, right? And so for this reaction, it said they actually trapped the oxygen and took the mass. So the mass was 14.9 grams. So the percent yield, in this case, let me just add another page and not try to squeeze this in. The percent yield in this case is going to be the actual, which is 14.9, divided by the theoretical, which we just calculated to be 15.84. All right, so percent is 14.9 grams, and that's why the theoretical has to be in grams. Hey, Ms. Campbell. I'm okay. Teaching. I got doing class. Yep. Okay. So 15.84 grams, and grams are going to cancel, and that'd be times 100. Can we get that calculation real quick, somebody?
That's 15.84 on the bottom, right?
Yes, 15.84 in the numerator and 14.9 in the denominator.
I got a 94.07.
So we'll say 94.1%. Yield for O2, right? So anytime you do a reaction, the yield is important, right? You always want to calculate the yield, and you can estimate how much you're supposed to get. That's the theoretical. And then after you do the reaction, and we're actually going to do this next week, not this week, because Wednesday, I think today that lab is going to be stoichiometry with copper sulfate and iron, converting that into copper and iron sulfate. So that's today for Wednesday, but that'll catch everybody up. So next week we're going to do a limiting reactant lab, where part of it is calculating the theoretical yield as well as the percent yield. But we first have to figure out which reagent is limiting. All right, so with that, we can calculate percent yield for any reaction. All we need to know is what the equation is for the reaction and how much we started with of both start materials and which one is limiting. If you know those three things, you can calculate percent yield for any reaction. All right. Any questions about that example?
No, sir.
All right. Let's go to the next one. We got another example right here. I actually had to alter this problem. I found it, but I couldn't use it in the form it was in because the actual yield was too high. Your actual, your percent yield will never be more than 100. Right? It'll never be more than 100. So anytime you have a theoretical yield that is greater than your actual yield, then you're gonna have a problem. I'm sorry, that's less than your actual yield. You'll have a problem. Your percent yield will never be more than 100. It's gonna be anything from 100 down to 0.001, but it'll never be more than 100. It can't be. That's not possible. All right, so let's take this reaction right here, and let's read the question. It says use the balanced chemical equation below. If 40 grams of acetylene and 65 grams of oxygen are used, and 12.5 grams of water is produced. Let's go ahead and get this out of the way. This is my actual yield. All right. So it's telling you how much water we get. So what we're gonna do is calculate the theoretical yield, right? And it's asking what is the percent yield. So we don't know the percent yield until we calculate the theoretical yield. Right now, in this case, we're going to have to determine which, because there's two reactants. We got to figure out which one is limiting. Because we don't know. Right? And it's very tempting to look at those coefficients, the 2 and the 5, and say, well, 2 is less than 5. So that must mean that reagent is limiting. We cannot do that. You have to calculate the percent yield. And in order to do that, the limiting reagent. You have to find a limiting reagent in order to find the theoretical yield. You can't just assume based on the coefficients that something is limiting or not limiting, right? So in order to do that, first thing we need to do is get everything in grams, right? So in moles. So we're going to determine, because the question asks us the percent yield. Before we can get to that, we got to know what the limiting reagent is. So we need to determine what the limiting reagent is. I'm just going to abbreviate that, right? First thing we got to do, everything here is in grams. We can't work with grams when we're trying to figure out what's limiting, right? So we need to put everything into moles. All grams have to be converted into moles. So it gave us 40 grams of acetylene. And it also gave us 65 grams of oxygen. All right, and we need to figure out the number of moles for each one. Well, acetylene, we're just going to divide that by the molar mass. We can calculate it. We don't even need to know it. 2 carbons is 24, 2 hydrogens is 2. So that's 26 grams per mole for acetylene, and that's going to give us moles. Here, we're going to take that and divide it by 32 because we have 2 oxygen atoms together and it's a diatomic. All right, so that's 32 grams per mole. All right, so what do we get for 40 divided by 26? Should be 1 point something.
Uh, 1.54.
Okay, so 1.54 moles. And then here is 2.03 moles. All right, so that's for acetylene. So this corresponds to C2H2. This corresponds to O2. So now, once we find that, those numbers of moles, we can figure out how much it's asking about water. It's asking about the percent yield of water. We can figure out how much water each one of those is going to produce, right? All we have to do is take those moles, use the stoichiometric factors from the equation to convert moles of one into moles of the other. So here we want to take this and we're going to calculate the moles of H2O formed from each. Moles of H2O formed from each one. All right. So let's do that. Let's take the I don't know why this thing keeps disconnecting. Hold up. I think I see the problem. I had to change internet sources right quick. Give me 1 second before the screen times out again. Okay. All right, we still on. And the screen is still visible, yes?
Yeah, we see your screen. It's just not on Zoom or on a board.
We're gonna take, okay, all right. So we're gonna take 1.54 moles of C2H2. And from the equation up top, we have from the equation up top, we have 2 to 2 ratio of water to acetylene. So we're going to say 2 moles of water divided by 2 moles of C2H2. Started raining all of a sudden. All right. So that's the setup. The 2's are going to cancel, obviously. So we'll just be left with 1.54 moles of water. Right. So that's the setup for that. And then once you calculate it, you can see that you got 1.54 moles because the 2's it's the same as saying 1 to 1 if it's 2 to 2. All right. Now let's figure out how much water oxygen will produce. So it's going to be 2.03 moles of O2 times, if we look at the equation, what's the ratio of oxygen to water? All right, look at the coefficient in front. There's a 5 in front of oxygen. There's a 2 in front of water. And we want to cancel oxygen. So we're going to put the water in the top again, 2 moles H2O divided by 5 moles of O2. All right. What do we get from that? Anybody?
0.812 moles.
Okay. So based on the coefficients, again, had we assumed that acetylene was limiting because of the 2, we would have been wrong, right? Because you see right here that acetylene gives me almost double the amount of water that oxygen does. So in this case, oxygen is my limiting reagent. So oxygen is limited. Questions about that part? We're not done with this question yet, but are there any questions about this part right here?
No, sir.
All right. So oxygen is limited in this case. And now we can calculate the theoretical yield based on that. So now we can say that since oxygen is limited, we can calculate theoretical yield based on that fact. So I'm going to say 0.812 moles, right, of O2 sorry about that. That's a H2O times 18 grams per mole, right? Because the water itself is my product, and it has a molar mass of 18 grams per mole. So when you're calculating the theoretical yield, it's the moles produced times the molar mass of the product, right? So that times the molar mass of water, which is 18, it's going to give us somewhere around 14 grams. Right? And remember, the theoretical yield is always given in grams. So that's why I have to go back and take the moles from the limiting reagent and use that to calculate the mass of water based on that number of moles. All right. So now let's answer the final part of that question, which says to calculate the percent yield. Which is actual over theoretical times 100. The actual is up top. It told us that we got 12.5 grams of water. It's gonna be in the top, 12.5 grams divided by 14.62 grams times 100. All right. So 12.5 divided by 14.62. That's about 85.4% yield. And just to recap it, all of my yields are going to be basically hinging on what the limiting reagent is. So whatever that limiting reactant is, that's going to control the theoretical yield, which in turn is also going to control the percent yield. All right, questions? Any questions about that? Any questions? All right, let's look at this last one. I'm actually going to leave this until tomorrow. We're going to stop a little early. So it's giving us, and I want you to work on this, and tomorrow we'll discuss it. 100 grams of CO and excess H2 to form 75 grams of CH3OH. And here's the equation. And it's already balanced. The question is, do you have to calculate limiting reagent here? Why or why not? Let me ask that question. Right, if we read the question and it says that H2 is in excess, what does that mean? We talked about this Monday. If one of your reagents is in excess, what does that mean for the other reagent by default?
I can't remember exactly what it's called, but it means that the other element is the
It's limiting.
limiting agent. I think the word is agent, right?
So this is limiting. If this is excess, the other one by default is limiting. And since the problem tells us that H2 is in excess, that means that our theoretical yield and everything is going to be based on CO. All right, so I'm gonna leave that. I want you to work on this problem, and somebody can come in tomorrow when we begin and walk us through it. All right, any questions about anything?
I have like one question.
Go ahead.
So when I took the test, you said that what was it? The little balancing equation sheet was due whenever the test was given to us. When I tried to turn it in, it didn't let me. It was like it was closed off. So I was wondering if I could just email it to you, or are you gonna like reopen it?
Nah, don't email it because I got enough stuff in my inbox. I'll just open it back. I don't even think I closed it. It should still be open. But if it's not, I'll check.
I couldn't open it. It kept saying server unavailable or something like that.
Oh, okay, yeah. That's not because it was. I think Blackboard was down. But check again today and try to upload it. And if not, just text me or email me, and I'll make sure it's open. But please don't email it if you can help it, because it's gonna get lost.
All right, appreciate you.
All right. All right. Any other questions? Everybody good?
Yes, sir.
All right. Y'all have.
I have a quick
thank
question.
you, Anya. Oh, sorry about that. Thank you, Anya. I didn't see the
No, you're okay.
I didn't see your chat, but thank you. Yeah, with the iPad, I can't see when messages come through. So
I figured you're fine.
Yeah. All right, go ahead. Who else was that? Getting ready to ask a question.
It's Sierra.
Come on.
Can we go ahead and turn in the resuscitation?
Oh yeah.
I know it's late. I know it's one we recently was supposed to do. I think you did a video on that, and then it was one before that too.
Yeah, turn them in.
Okay.
Everything is still open at this point.
All right. Thank you.
Yep. All right. Anyone else? Everybody good? All hearts and minds clear?
Yes, sir.
All right. All right. I'll see you all on tomorrow, God willing, and work through that last problem so we can discuss it at the beginning of recitation.
Thank you.
All
Have a good day.
You too. Y'all take care. Have a good one.